Perfect. Okay, so good evening, everyone. Welcome to CADSEA August Spotlight Talk. Tonight, we are looking at how the company are really making use of the data with their AI, like turning database into a natural conversation with text to SQL and using RAG to unlock unstructured knowledge, choosing the right model through the evaluation, and even helping AI understand the complex chart and the large report. We are so looking forward to that. I'm your host tonight, Ivy. I'm a data scientist from Capital One. So without further ado, a little bit about our CADSEA. So CADSEA, we founded in 2019. We are dedicated supporting data professional across the DC, Maryland, and Virginia area. Over the years, we have hosted more than 20 technical talk, multiple annual events, and we have reaching thousands of individuals. So right now we have mainly two main program. The CADSEA Tech Formula is today, and we have CADSEA membership. So this is CADSEA, and we will continue to hold a lot of events. If you are looking forward to join our community, please screen the QR code, and then we can make our conversation there. Also, we want to thank you for our sponsors for their support for this event. It is their support to make it happen. Thank you for the University of North American, Intango, and the Premium Dental Art. Also, we want to thank you for our volunteer. It's your dedication make this event possible. We have volunteer for marketing, for the post, and for all for this event. And before we started, we want to have an announcement that is for our next workshop. It is for a communication workshop. It is about how to become a 4C data science speaker in the AI era. It is about compassion, collaboration, creation, and communication. It will be taught by Mike Nie in September the 6th, 2 to 4 p.m. For more details, please screen the QR code in below. Okay, without further ado, I want to welcome our speaker today is Bethany Wang. She's the CEO of Precur AI, the former research for the Google Cloud Vector AI research and the Gemini reinforced learning and model tuning expert. Today, she will walk through us how the enterprise use AI and dive into a real use case. We are so looking forward to it. So please join me to welcome Bethany Wang. Bethany, this floor is yours.
Thank you. Thank you so much, Ivy, for the wonderful introduction. And really happy to meet you, everyone. An honor to be presenting to you and looking forward to more communications. Let me screen share very quickly.
And Bethany have told us she is happy to take any question real time. So if you have any question, just feel free to text it out in the Zoom chat. I will monitor that. Thank you.
Let me know if it's showing up. Okay, perfect. Thank you for the intro. And today I'm very excited to deep dive into the AI in enterprise reality, including three aspects: model, data, and workflow. So at any time during this, please feel free to interrupt with any questions that you have. Very happy to take them. And Ivy, please monitor the chat. If there are any questions, feel free to interrupt anytime. We'd love to also have a Q&A at the end of today's session so that we can more deep dive into the use cases. Myself, I'm the co-founder and CEO of Precur AI. Prior to that, earlier this year, I left Google and I was at Google Cloud Vertex AI and leading the Gemini fine-tuning and reinforcement learning effort, especially for enterprise users. So we have a service for all enterprise users on GCP, and including evaluation services as well. Very passionate about real-world use cases of generative AI in enterprises because it's very different than academic benchmarks. in particular, much more messy data over here. And I know that if you have worked on enterprise use cases or you are, it's like very different, like the ideal world versus the real messy world. So really happy to do more deep dive into it. Agenda today, we'll talk about 3 aspects from the model, the data, and the complex workflows. I'll dabble on the model part for 10 minutes. The goal is to set the ground and also have a common set of terminologies that we will refer back to as we're deeper into the talk. And then we'll talk about accessing the data, including the structured data via text to SQL and unstructured data via RAG. And also there are pitfalls as well. Finally, we'll go into agentic workflows. Those are multi-step tasks by stitching together a lot of the components that we will describe in earlier parts of the talk, and in particular dive into some open questions. Agents are important because they are really delivering value in enterprises, but also we observe that there are a lot of difficulties that enterprises are facing, especially in agent applications. So let's dive right into it. Model selection, the first part. We'll talk about 2 types. One is long context and the other is thinking. And finally, I'll give a few example models to look at together. So this is like this is a very good old familiar transformer architecture, just to align everyone. This is a classic like decoder only prefix LLM. You have the prompt, you have the decode, which is the target. And how it works is that every time you have a token, I'm just using the word here for convenience, you have a token in and the next token prediction out, and you stuff the next token prediction into the transformer again and get the next token, etc. And finally, when you're completed with the sentence, it spits out a BOS, which says, okay, language model, now it's your turn to either complete the sentence or make a response, etc. So this is like how the decoder only prefix LLM, which is the most almost the most popular architecture these days for most large language models on the market. And I want to talk a little bit about the attention mechanism, because this is also very related to why long context models are very hard to train and some of its limitations. We all know that the attention is quadratic in terms of compute complexity with respect to context length. And the reason is this shows the self-attention. You have one word attending to every other word. And therefore, if your context length is n, in order to decode the n+1 word, the complexity will be quadratic in terms of how big n is. So it's an n-squared problem. There are optimizations you can do in terms of not multi-head, but like multi-query attention or group attention, etc. But ballpark-wise, the complexity is pretty high. And this is like some tricks that can be used to optimize the attention, which instead of a dense attention, which I said is like n-squared, you can like do local attention, which I only attend to a small window of words in front of me, before me, or I only attend to like hops of words before me, or some smart routing mechanism that you could train to have the attention for. And why do we talk about this at all? It's because it's taken a lot of resources to train because of how big the model can grow. And during training, the reason is because during training, you need to hold several things in HBM. So HBM is like the RAM but for GPU. So you can imagine like for larger models, in order to load all of the parameters into the GPU, you would expect the GPU to have a bigger memory. And GPU memory is pretty expensive than CPU RAM. So in order to train a 3 billion parameter model, you get most of the spaces in the RAM gets taken by model weights, which takes around 6 gigabytes for a 3 billion parameter model, assuming the FP16 training. FP32 would take even more, like twice as more. You need to hold the model gradients. You need to hold the optimizer state, which is big. And also you need to hold some other models like reward models if you were to like use reinforcement learning, etc. this sums up to 36 gigabytes in total, and plus some overhead like activations intermediately, and also the computation, like the code. The code is compiled into a computation graph using JIT, whether you're on PyTorch, on JAX, etc. It gets compiled, and then also takes up some portion of the HBM. So in total, a 3 billion model usually takes and easily takes like 50 or 70 gigabytes, which requires one chip of H100 to train. So this comes to the question of long context models. Long context models, like 1 million context, those models are not trained using 1 million context. And the reason is, like, if you train on such long context, it's impossible for the hardware to hold that many weights, because you don't have so much hardware to be training over. And therefore, usually, oh, thank you for the marking. And therefore, usually 1 million context does not mean that it's trained using 1 million context. Instead, it deploys some tricks during training. I wouldn't get too much into the tricks. I think each company's proprietary models deploy different mechanisms for training to simulate this long context behavior. But also, not just the hardware limitation, there are not so many training data points that are 1 million context. Maybe some long proof or some long history of a person or novel could be very helpful resources, but it's very hard to obtain long context samples. So those pieced together constitutes the fact that long context models are not actually trained long context fashion. And therefore, you would find that 1 million token context models, their effective context, I mean, by that, I mean, they can effectively reason over and understand around 100,000 or somewhat that range of the quantity of tokens. So next time you you use long context models, I think those are some of the pitfalls that we want to avoid as well. Problems include lost in the middle. That means, like, if you have a very long input, then things in the middle tends to get neglected. And context rot. Context rot refers to agents as they grow longer in context. It kind of poisons its own context because it's getting too long and things get forgotten. And also, it's easily distracted when context gets long. You see a lot of benchmarks like needle in a haystack to measure the long context quality, but actually it's far more than enough usually. The reason is because needle in a haystack usually works in the following way: that you have a salient sentence that you need to get, that is the needle, and you have a lot of distractions in the sense that they are like other random tasks, and your task is to get the salient sentence out of 100 like different things that are concatenated together. So needle in the haystack is a fetching, like finding stuff task. It's not a reasoning task. So finding has a very different difficulty level compared to reasoning. And when we see the reasoning performance over long context, this is taken from GSM Infinite. So it is a benchmark coming from CMU, saying what is the performance of language model in terms of the growth of the context length. You see that when context length grow, so on the left side of the diagram, zero context has reasonably good performance for QN 2.5 model. And then as context lengths grow, when you grow to 32K context, the performance, I mean, the accuracy gets worse significantly, very quickly. So this is to say, like, it's not, and it's just 32K context. It's not even 1 million context. The problem setting of this paper is that it has GSM, it has the grade school math problems, and it has like several hops of reasoning in order to get an answer. By reasoning, for example, there are X number of animals on this farm, and the number of animals on that farm is like Y plus the number of animals on this farm, etc. So it has this type of reasoning chain that the model needs to figure out. Plus, it has a lot of noise that is added to the context to make it more difficult for the model. So what we see is when context grows long, the reasoning capability degrades very, very quickly. And now the second question is, does RAG help? in this case, even RAG is not to the help, because on the right-hand side, you see the performance of, so this is like, I believe this is taken on 8,000, so 8,000 token context length. And you have the blue line, which is the language model itself, and you have the orange line and green line, which are like iterative RAG and the RAG, like vanilla RAG itself. Both are susceptible to long context. So what I'm saying is long context is a perplexing problem up to now. And when you're choosing language models, don't just trust it has 1 million contexts. You need to measure for the effective context. Usually it's much, much shorter than 1 million. And then we come to another type of model, which are increasingly popular, which is the thinking models. The thinking models is fundamentally trained by inducing the reasoning behavior of language models. And by that, I mean, previously we talked about long input, that is the long context. Thinking model, you can think of it as long output. So essentially it is helping the model to decode very, very long. That is to say, instead of spitting out an answer up front, can you like think for many, many tokens? And during thinking, it indeed is pretty helpful for the model to decompose the problem. The reason is actually a simple answer would be compute. During thinking, during the decoding, you're essentially utilizing more compute in the language model. You're utilizing more flops. So more compute means like better performance. But moreover, like the thinking model is usually trained by, trained by using RL and give it a positive reward when it's like decoding longer sentences and achieving the goal at the same time. So you would imagine in the reinforcement learning phase, you have a task that is scoreable. But instead of just scoring on the task itself, you would like score also based on the length of the decode, so the length of the output. And this way, you're assigning positive reward and encouraging the model to decode longer and longer. And usually, it's very similar mechanism as chain of thought. So usually the model learns over time to comprehend the problem, to decompose the problem, and finally to have a higher probability to get to the correct answer. And also, it has interesting behavior in tool use as well. For example, this is like one real use case for financial QA. So how would you adjust the EBITDA or PE multiples for something? And then the model, if it's a thinking model and if it has access to tools, what it would do is to first spit out a thinking trace. I need to research A, B, C. And then based on the thinking trace, it decodes a tool use token. And then it starts to call the tools, including the tool name, tool parameter. Like in this case, the tool name is search. The tool parameter is the queries you would input to the search. And finally, tool responses. And then it starts a second round of thinking of, okay, I guess the responses, that's great. Now, what are the second round of questions I can ask to get even further information in order to answer this question? So this is like the long output behavior that you are inducing on the model, and it's conducting multiple rounds of thinking, multiple rounds of tool calls, and in this way, getting a better response usually over time. So I'll pause here for any questions or like follow-ups.
Yeah, I have a quick question. Yeah, so
Yes, go ahead, please.
yeah. So I'm Ivy. I have a quick question. So for all the tools, so do we have like a tool list for all this tool, or like what's the backend tool they have that they can utilize for this language model?
That's a fantastic question. So let me actually jump ahead a little bit to the tool use, to the agent and tool use. Let's see. This one. Tool use is particularly challenging in real settings for enterprises, as you said. The reason is because in real world, enterprises have hundreds or thousands of tools, not just like 10. And how the tools get injected into the language model is usually, at least for Gemini, how it does it is that, so you have the prompt, you have the system prompt, you have the user prompt, but also you have the developer prompt section, developer instructions. And what developer instructions look like is that if you have, oh, sorry, why am I jumping ahead? Sorry. It is a concatenation of many tools and their descriptions. So usually a tool is described using some schema, let's say Open API schema, etc. Other schemas are also applicable, and what schema is the most suitable depends on what schema the language model you're using is trained over. So let's say for Gemini, it is trained over a specific tool schema. I believe there are some like meta tokens that they inject internally. Then you would expect that during the tool call, just when you like give it 10 tools, it'll be inflated. It'll be inflated into the tool description, the tool parameter description, and concatenated together into the developer instruction section, and it gets appended to the prompts that go into the language model. So the language model, because it sees these tools you have, and it has been trained to be able to do tool call, it'll be able to decode that tool bracket. So the tool brackets token, meta token is what you see at the beginning of the tool call. It'll be able to decode that meta token, and then it'll start to decode furthermore, like what is the tool name, what is the tool parameter, etc. But as you said, like enterprise tools are hard because it has like hundreds of tools and tens of parameters per tool. And usually the training data is non-existent in the language model, public training data. So the model has never seen a lot of those type of tool before. And that makes like enterprise settings tool calling pretty challenging. But to answer your question, this is how language model call tools.
Thank you. Yes, okay. So I think in your later section, you will talk about how this agent can decide which tool to use, because if we have 500, maybe they need to use some search, or like, I don't know, maybe they have a rack over there to choose the tool, or they have some other like rule-based model to design the tool. But I got the point. Yeah.
Yeah, indeed, as you said, yeah, there are tricks in terms of how to deal with that number of tools.
Thank
My
you.
computer is a bit frozen. Sorry for the delay.
No worries. I think we are going back to the
Yeah.
section 1.
Would you mind if I stop sharing and share again?
Yeah,
I
no
think
worries.
it's kind of frozen. Thank you. Let's see. No, my Chrome is completely dead. So
Or if you need
maybe,
to restart, or take your time, no rush.
or maybe Tiger, could you help me present? I
Yeah.
sent the deck earlier to you if it's possible. Thanks.
Yeah, Ivy, I actually just forwarded that to you. And I'm trying to upload this to my current laptop that's on here. Let's see who's faster here.
Thank you. Okay, maybe maybe I can present. I'm back. Sorry.
Yeah, we can see your screen.
Perfect. Perfect. And we talked about like long output and rewarding long output for thinking models. We'd love to bring to your attention a few example models to watch if anyone is looking for some reference points on model choice. These are like some models that I've tried before and would love to share with you. The newest would be like GPT-5 series. It contains both thinking and non-thinking models, pretty well-rounded. I think they added a lot of the tool use data into the GPT-5 training, so it's much better than 4.1 as tool use. And in terms of context length, it's about 200,000 context length, pretty decent for enterprise uses. 2.5 flashed for Gemini. It is a really high ROI model. So in terms of high ROI, I believe the input is like $0.3 per million tokens. In comparison, GPT has much more expensive. I believe GPT-5 mini is like 1.25 per million tokens. Gemini Flash has a lot of the tool use data trained into it. It's also long context. I believe it's 1 million. And pretty fast in terms of response time as well. It allows you to control the thinking budget explicitly. So if you want to be more, make it like faster, etc., you can set thinking budgets to none, so disable thinking. But also you can control letting it have 1,000 tokens for thinking, 4,000 for thinking, etc. To speed up your inference time, but also lower your cost for decoding. O4 Mini is a very powerful model. A lot of the tool use data trained into it. We measured it's much better than O3 in terms of the tool use capability. It is a thinking model and it's powerful but pretty expensive. GPT 4.1 Mini, this is the longer context model than GPT-5 series. I believe it's 1 million context. And it's like not that expensive either, but it's the non-thinking model. So yeah. Claude 4 series is really powerful in coding and also in tool use. I have friends who he was making bio agents and he measured that Claude 4, and they're actually in collaboration with Anthropic. Claude 4 tool use capability is actually pretty impressive and compared to other models. QM3 is a pretty good series of models. It comes in different sizes and flavors. There are MOE models, which are the big one is like 200 billion parameters with 22 billion active parameters, meaning like at any time on average, only 22 billion parameters are activated, and therefore like it's much it's not that the entire 200 billion are active at any time. That makes it much faster in inference. But also it has dense models from 32 billion all the way to 0.6 billion, so that they have extremely small models and pretty fast for inference as well. I tried the 1.7 billion model, pretty decent in terms of quality as well. I think it's pretty good ROI as well as an open source model. GPT OSS is the latest like open source model by OpenAI. It has two models, 120 billion with 5 billion active parameters and also 20 billion with 4 billion active parameters. Both are thinking models. I don't know if you could disable thinking for them, but you could give it a try. Pretty good performance. We've used it as a reward model and it's performing pretty well. Those are the latest models. Some of them you could watch, but of course, like there are hundreds of models on the list. But just to provide people with a starting point. Yeah. Then we come to the data part. The challengingness about enterprise is the raw data is a far distance from being able to be used by AI. In particular, two applications of interest, and we'll spend more time on it, is text-to-SQL and also RAG. Real enterprise text-to-SQL is difficult. The reason is because usually the table is very wide, hundreds of columns, but also the columns requires pretty much domain knowledge. Because the column naming is not very telling. Usually what people do, and I believe a lot of you have already tried it, is having a semantic layer on top of it. That is to augment the columns with column explanations. This includes what the column name means, what is the correlation between different columns and different tables, but also what are helpful is few-shot few short examples with historical and relevant queries. In this setting, at least observing with Looker folks, fine-tuning usually helps a lot in terms of having a domain-specific model that is for your enterprise on your database. The several data sets to watch are Bird and also Spider. I believe Bird is a pretty, I think it came out like 2 or 3 years ago, and it's a little bit more saturated by the recent model advances. Spider came out this year or last year, I think it's this year, and it's more challenging text-to-SQL gym that you can play in. This diagram is actually taken from the Spider paper. And it describes like a text-to-SQL setting that you'll usually end up in. It's not just the databases you have or the schemas, but also the documents, like the database's metadata, and also external knowledge, and also the code base that includes the past queries you have issued on the database. And then these all constitutes the raw materials you could input into your language model, expecting that it can output a SQL. There are lots of rags or tricks that we'll go into in more details afterwards. But one thing I would really love to underscore is that if you have historical queries, you have an unfair advantage for text-to-SQL. Because a very simple and intuitive example would be like, how would you query from a simple table of countries' GDP? Like, do you select from where the country equals France or where the country equal FR? I'm having this example here just to say that it's very hard to write a query without knowing the data or without knowing how previously people have written the query. What some people have, and it's very effective, is that some people use supervised fine-tuning on past queries in order to do it. I believe GCP back at Vertex, we helped quite a few clients do the supervised fine-tuning on their text-to-SQL tasks. It indeed helps quite a bit. I believe the accuracy is up from 70% to around 90%, almost 90%. So it's a pretty effective technique usually. But in terms, so how supervised fine-tuning works is that you have input target pairs. Input is the natural language description. Target is the SQL, that's the output. And then you perform almost like distribution match in the sense that you want to maximize the probability of decoding the target conditional on the input. So there are a lot of supervised tuning packages on the market, including open source ones. And I believe some companies, I believe GPT and also Gemini, both offer supervised fine-tuning offerings that you can directly use. Curating the dataset is key in this case. But also, we're talking about agent loops as well, not just a single turn text-to-SQL. And agent loops is here is where things gets interesting, because you're not just generating the SQL in one go, but you're interacting with a code sandbox. And that sandbox, is that it executes the query and gives you either the response or an error message. And what it does, how it works is usually a question in LLM agent. In this case, it's just an LLM. Spit out SQL or Python code as you usually would. And then you would execute it on a code sandbox and get the response messages. And then the response messages gets back to the LLM agent. And then the LLM agent can think again and say, oh, do I need to change the query in a little bit? Or do I need to, there are a lot of things that it can do. We'll see very, very shortly before it outputs the final result. One particular thing you could do is RLEF, with reinforcement learning with execution feedback. And this is actually the diagram is taken from a paper, but the concept is not new. It's been there for a long, long time. since the foundation model company started working on like, code execution and code generation. So what's going on is that you have natural language description goes into the LLM spits out a solution, and it gets, if it's not exceeding the turn limit, then we get a reward signal back from the code sandbox. The reward signal, it consists of multiple parts. We'll talk about it in one bit, but the reward signal kind of gives the LLM an idea about whether it has generated a good sequel or whether it has generated a horrible sequel. So you would, a real example would be like write a code solution for a problem X, and then the LLM will write a solution, and then it will get some feedback, and then it'll go on and do a second round of solution by modifying the previous round of solution until it passes. And how you do it is, I'll showcase here a very simple setting of the RL environment. So you have an agent, which is what we call the policy model. It's just an LLM. And you do back propagation into the weights of the LLM usually. And it has an environment that it's interacting with. In this case, it is the code execution sandbox. The role of the environment is just to execute the code so that it can give the reward signal back to the agent. So this constitutes the loop of a policy model take an action, observe a reward from the environment, and then it updates its weight. But if it's multi-turn, it'll do like multiple rounds before updating its weights, and so on and so forth until it reaches the end of an episode. By the end of the episode, I mean it either runs out of context length, or like it runs out of the maximum number of turns it can have to play the game, or it successfully arrives at a working solution. The reward design is key in every reinforcement learning problem. And the reason is the following. Usually for code execution, like text-to-SQL code execution, you would not only have the execution reward, but also have some sort of semantic reward as well. The execution reward is important, whether the code passes or whether the code fails. But what we observe in some cases is that if you just like use the execution reward, the model will sometimes take shortcuts, like it guesses something, or it simply writes a function without the function body. So it writes a function just says path, and then the code will never crash because it does nothing. But it's kind of a trivial solution that we don't want the model to end up at. So what I'm saying is this type of binary reward is helpful, but it's susceptible to reward hacking behavior. And therefore, usually you could amend it with a semantic reward, which is the code semantics. Like ballpark-wise, given the query, given the code, does it look like the code that can solve the query? We'll talk a little bit more about it in one bit. So like these two reward having a linear combination between these two constitutes the final reward. But of course, you can have other reward heads that you would like and add them all up using some weights. And then this gives you a good reward signal to back propagate your model with. In terms of the code semantics, so the second reward that we talked about just now, it is pretty often you could implement it using an LLM judge. So what it looks like is it's just a prompt that goes into an LLM judge. We sometimes call it generative reward model, but what it is, it's really just a query. A query that the model that the user wants to accomplish. Maybe the correct code that you have from historical context, and then the new code that the model has generated. And the LLM judge is saying, oh, given the query, given the correct code, given the new code, does it look like a code that can execute and then gives the expected reward? And then it assigns a numeric score to this triplet. And then the numeric score is as a reward fed back into the model so that the model weights get updated. So this is like how the RL, we talked a little bit about RLEF, our execution feedback, with the reward design for execution, reward design for code semantics, in particular for text-to-SQL setting. And then this could be a very effective mechanism of you having a model that is tuned for your enterprise text-to-SQL tasks. I'll pause here for any questions. Okay, we can move on to see a example here. So this is just an example of like inducing the multi-term behavior in your text to SQL setting. This behavior, a lot of the thinking model has this behavior of think, tool use, and think, and this can be further induced using the reinforcement learning method as well. So you see that it's thinking that I need to compute X and Y amount in order to answer the user query, and then it uses the tool for SQL execution. And then sometimes the tool just outputs the wrong SQL. And then you would get a tool response. We talked a little bit about the code execution sandbox that will give you a response, give you an error signal. And then you think again, and then you call tool with another query. It may be the same query rewritten, it may be the same SQL rewritten, or it may be another SQL because the model has learned to think, oh, instead of just writing the SQL, maybe I should preview the table of selecting from the table, limit 3 rows. And this way I can have a better idea of what the data looks like before I even go ahead to write the query. So this type of peeking the data and then writing the SQL query, so this type of good behavior that you want to encourage are all able to be induced using your reinforcement learning algorithm. I want to talk a little bit before we talk about RAG, about the time series foundation models. Myself is not working on this, but my sister team, they have worked on a time series foundation model for zero-shot prediction. I put it in here because maybe it's of interest to some folks over here as a type of special case of structured data. So in this case, you have a time series and your goal is to predict forecast. And what time series foundation model does is that instead of taking words as tokens, it has the time series patterns as tokens that they train a foundation model over. And the good news about this is that they also can decode something like this. So the idea is that as a foundation model, after you have seen so many types of time series, you should be able to capture some characteristics of the time series that you have usually seen. And this kind of fits a implicit predictor inside the time series foundation model that enables the zero-shot prediction behavior. I think they have the code on GitHub. They have a blog post about it as well. We'll share the slides afterwards and it'll include a link in it. You can look for them. And next we talk about the unstructured data part now that we talked a bit about the structured. The unstructured data part is what a lot of people would say retrieval-augmented generation, but also there are other methods to deal with it as well. I'll give a brief, very short crash course on retrieval-augmented generation before we dive into more detail. So what it is the following. Here's an example of, let's say I have a website. I want to build a chatbot on my website that answers customers' inquiries about all the FAQs, the documents that my website has. So usually what people do is have your website and then do a spider and crawl on your website and then have the document ready, have the indexing ready by chunking and feeding it into embedding models, and then feeding it into and then feeding it into a document retriever as well. And then so this is like the indexing phase. The second row here shows the query phase. So the query phase is like in real world, when a query comes in, like what is the MSRP for F150? You get a query rewrite, and then it gets fed into the retriever, and the retriever spits out 10 or 100 documents that are relevant. And then you further feed the relevant documents into the document summarizer model, which takes into conversation history into account as well. So we have this state tracking for conversation context. And then it spits out an answer in a conversational way by taking into account what the user's past conversations are, taking into account what the retrieval results are, and then spit out an answer that is helpful for the user. A little bit of zooming in is that, sorry, the slide is just the second row. It's just the second row of the previous slide. During this serving stage, you usually also, what you do is to rewrite the user query into a set of subqueries and do the retrieval using the subqueries and finally concatenate all of the results. And then what usually follows this is a re-ranking stage. That's where you see there are lots of re-ranker models. But what re-ranker models are is that they take 100 documents that are retrieved by the retriever and they rank them by comparing the comparing the relevance score of those documents to the query. And then they spit out a re-ranked set of documents, which you can threshold, like just take the top 10 that's coming out of the ranker and then stuff it into a language model for answer generation. This is the existence of re-rankers is for the sake of the fact that the retriever usually the goal is to have a high recall to like, surface anything they can surface. As long as you have a high recall, I trust the re-ranker to surface the right documents, to bubble the right documents to the top. And I can take the top and then I can return it to a language model for answer generation. So this is RAG, and if you put a loop on it, it becomes the deep research. The deep research is just fancy RAG with some reflection that's coming out of the orchestrator agent. So what happens is, you see, compared to the previous slide, it is very, very similar, except for the fact that after you have one round of retrieval completed, you have a reflection step of, are there any knowledge gaps that between what the user is asking versus what I have retrieved for. And then if there are knowledge gaps, you do another round of query planning. Sorry, it should go into the subquery. You do another round of query planning, do another round of subqueries, document retrieval over and over again until you have a satisfactory set of documents and answers that you can spit out to the user. So deep research is RAG done in an agentic way because you have this reflection and this like multi-round thing. But what's important is that you can, without fine-tuning, you can arrive at a pretty decent quality deep research usually in most of the cases. But if you're like really particular about the quality, fine-tuning or RL on the orchestrator agent helps a lot. The OpenAI's deep research, what they do is they collect a number of difficult web browsing tasks, and then they do this loop. But during the loop, they do also the fine-tuning of the large language model that is deciding what subqueries I should write. When should I query for when should I query for more information and how should I query for those more information, etc. So this RL for goal completion is pretty important if you want to arrive at a decent quality deep research application. And the way you RL is very similar to what we saw we discussed, you remember, we discussed a little bit about reinforcement learning with execution feedback. The way we do reinforcement learning here is pretty similar to what we did before, is that, so you also want a reward signal somehow. Now the question becomes like, how can I have this reward signal in a numeric way? Usually when you have this type of pretty empirical results, like whether the retrieved documents are good or bad or what have you, what you would do is you would construct a large language model judge, or what we call a generative reward model, and have it like take in the snippets and then spit out a numerical score of the quality. So how to do a large language model judge is a whole nother topic on evaluation. We can talk about it a little bit today, but it's like it itself deserves a lot of like, deserves an hour. So yeah. Retrieval is usually the hardest, not the generation part. And the reason is because generation is a summarization task. It's pretty well understood and has a lot of training data in the language model itself. However, retrieval is answering the question of, you have a data lake, how do you surface the tiny bit of information out from your gigantic data lake? usually retrieval is the hardest, and there are several culprits that I would love to like call out as a next step that you could avoid, and maybe we could have a follow-up discussion about how to circumvent or have some, new methods to do so. Some retrieval, what you usually see is it's a mix, what they call hybrid retriever. A lot of retrieval systems are implemented like this. I think Zilis is implementing hybrid retrieval. Vertex has hybrid retrieval, etc. What it is just a hybrid of dense and sparse retrieval. Dense retrieval means you have the vector embedding for the query and for the document. And then you compare the L2 or inner product similarity between the query vector and also the document embedding vector, and you take the most similar and then you spit them out. Sparse retrieval is the tried and true Elasticsearch and BM25, etc. So at the end of the day, you merge those results with some proportion, and then you do a re-rank over all of the things that you have retrieved. Yeah. A little bit more about the embedding models is if you're ever picking an embedding model on the market, most of them are trained in the following way. Most of them are trained using contrastive learning, meaning this is a 2015 paper saying this is a triplet loss that it introduced. So you have an anchor point, and your goal is to make the positive point closer to the anchor point and the negative point farther away from the anchor point. So the loss function intuitively you construct is that you want to maximize the delta between you want to minimize the fact that the distance between you and the positive point minus the distance between you and the negative point is bigger than 0. So you want to mitigate. You always want the positive point to be closer than the negative point. And if this is not the case, then you would penalize according to how big the delta is. And usually contrastive learning is followed by a set of other like supervised learning tasks, but that's not important. And then it gives you a embedding model. So what they do is usually, for example, I believe some of you have used E5 embedding or something like that. It is a transformer basically, and then you train the transformer using this contrastive learning task. And what you take as embedding is you do an average pooling over all of the output layers. Or some people would do just the embedding of the EOS token, so the final token. Or some people would do some fancy variants, like the embed is doing another attention layer on top of the final output layer, etc. But the idea is very similar for the embedding model training. So what you get, as you can imagine, because you're using contrastive learning, what you're getting is things that are semantically more closer to each other gets like more closer in location. And things that are further away gets more like further apart in location. But it has its own culprits because like when you think about contrastive learning, it's like trained on general concepts, like whether your company's knowledge is having the same meaning as general meanings, like whether your company's knowledge distribution is similar to general knowledge distribution, it's a question mark over here. Re-ranker models are also very popular and essential for RAG. And what you have re-ranker models on the market, they are usually like fine-tuned large language models. And those large language models are fine-tuned in particular for this ranking tasks. Some re-rankers like Cohere re-ranker, they are tuned using the list-wise at least as of last year, they're tuned using the pairwise ranking loss. So what you have is very similar to other like pairwise losses where you have a pair and you spit out a score. You have another pair, you spit out another score, and you maximize the delta between these two, knowing that one pair is better than the other. So in this case, you have maybe doc1 is relevant. Doc1 is relevant to the query, doc2 is non-relevant to the query. And then you want to maximize, like intuitively, you want score 1 to be larger than score 2, and you want to maximize the delta between them as well. So that's like some of the re-ranker models and how they're they are trained. Because it's a ranking problem, it makes sense to use the list-wise input to train a ranking order because the absolute value does not matter. Challenges in RAG are also very evident. You get one evidence challenge which is chunking, because chunking breaks a lot of the semantic logic. In my new company, we're working with clinical trials, and the thing you get about clinical trials is that it's a huge document, and the more important a clinical trial is, the bigger the document is. So the document has a lot of the parts, like the patient outcome parts, or the patient and the patient baseline, meaning like what conditions, what like disease or conditions the patient has, and how much intervention of the medicine they have been given. And the tricky part is that the outcome of the clinical trial is depending on the patient, like how healthy or like what condition the patient has, and it's depending on the patient's intervention. So you have this like unchunkable interconnecting logic in the document that it's very hard to reason about if you break the document into different pieces, into multiple pieces. So chunking is a big culprit, and constitutes to a lot of the problem, like piecemeal knowledge, like knowledge without the context that cannot be interpreted, or even conflicting knowledge, where you cut a piece of knowledge that does not have the condition, and then it seems to conflict with another piece of knowledge because like it loses context. There are several mitigations, including using overlapping chunks. I believe OpenAI's file store out of the box, they're using 800 as a chunk size, 800 tokens as chunk size, and 50% overlap, meaning for every document you have perfect overlap, like every document appears twice. But also you have mitigations like Anthropic's contextual retrieval, which is saying not only I'm chunking, but I'm attaching to each chunk some of the context or summarized things that I have with respect to the full document that this chunk is located at. Also, you have contextual embeddings. That is, so Voyage AI has this Voyage Context 3, which is a type of embedding model. But in addition to embedding the chunk itself, it embeds some information of the surrounding of the chunk as well. So there are mitigations, but overall they are for the problem that chunking is actually breaking a lot of the interconnecting logic. Me personally and my new company, we have done a little bit of research into this as well. So if you would like to chat more about it, very happy to. Also, another culprit is global queries. Global queries is, for example, find me all the clinical trials about a certain disease. And global queries are usually important because, especially for decision making, because you don't want to leave one out, because leaving one competitor out would completely sway your decision sometimes. And global queries is intrinsically hard for RAG because it doesn't have the notion of when I've like enumerated all of the relevant things in my database. Some people use a mitigation of graph RAG as a workaround. So graph RAG is saying, instead of doing RAG in a traditional way, what I do is I have pre-built an index that constitutes the communities. By communities, I mean it has for each document surfaced the entities out of those documents. And also it runs some graph algorithm over it to discover the communities among the entities that comes out of each document. And then so this is during the indexing time. During the query time, when each query comes in, like you would like ask each community to surface its answer, and then hierarchically, you would bubble up and then summarize the community's answer, and then further summarizes the upper level answer, etc. So you get this hierarchical thing that gives you kind of the global view of what the database look like overall. But of course, it also has some drawbacks, that the ontology, so the graph you build, the knowledge graph you build, is kind of predefined. For some use cases, it's fine. If you're just caring about the drugs, the disease is a cure, it's overall survival, it's progress-free survival. So there are just certain metrics you care about and they don't change a lot, that's fine. But if you have like very dynamic, you don't know what is important indeed in each document at all, then it becomes problematic because the ontology is hard to define in this case. Yeah. I also want to spend a little bit of time to dabble on the evaluation side, because eval is usually hard for language models. Sorry, I didn't spend too many slides on evaluation. If you want, I have more slides in the pocket, but due to time, like I wouldn't dabble more into it. Myself and my team, we built the evaluation, so Vertex AI evaluation for all GCP customers. And it's a popular service because everyone wants the success metric. A few tips and tricks for the evaluation are the following, and happy to double click in the Q&A session if you want to dive into it. Two types of evaluation fashions that we implemented. One is what we call side-by-side evaluation. The other is point-wise evaluation. So side-by-side evaluation's input is you have the context and you have the evaluation criteria. By criteria, I mean, let's say you want a complete answer that not only discuss about the methodology, but also discuss about the methodology's limitations. It's like alternatives, etc. So this type of rubric is what you could give the LLM judge with, and ask it to judge and ask it to judge almost like how we rate an interview candidate, how to score the answer given the rubrics. You would be as explicit on the rubric as you can, like score equals 5, meaning like perfect. Like you have like not only consider the method, but also consider its limitations, consider its conditions, etc. Score equals 4 means you have considered some limitations, but not enough discussion on XYZ, etc. So you want to be as explicit as possible so the large language model can be able to judge. So side-by-side and point-wise are both valid methods. You can view side-by-side as a competition of you have the question, context, you have the criteria, you have a pair of responses, A and B, and you ask it to judge whether A or B is the winner. So the goodness about this is that there are subtleties in the responses that can only be reviewed via comparison. It's like when you ask me to pick 2 dresses, both are very pretty. But if you ask me to like just pick one, like whether you want dress A or dress B, I would usually have an answer of which one I prefer. So side-by-side is for this nuanced cases where both answers are pretty good, but one is obviously slightly better than the other. Point-wise evaluation is the other. It's like just give you the dress and give it a score. Is it a beautiful dress? Is it a pretty ugly one, etc.? So you could view point-wise as bucketization and side-by-side as a ranking task. Yeah. So the goodness about point-wise is it's pretty simple, and you get a score out of it basically. And it's pretty absolute. So you can compare the scores among different dresses. But it has the culprit of, and it's not uncommon that both answers are score 5. Both answers are very, very good. Maybe one, yeah. So it's just hard to distinguish whether one is better than the other when you do the bucketization. So it has this granularity problem. And if that is the case, like side-by-side is usually to the rescue because you can compare the two, and it's usually helpful for model hill climbing. One small trick is that during evaluation, you want to do it multiple times and do a self-consistency over it. The reason is because for point-wise, you perhaps want to take the average of several times to make sure this is indeed the answer. For side-by-side, you want self-consistency to mitigate the position bias and also variance of the language model, because in side-by-side, you would have response A and response B, but also you want to swap these two and ask the language model, if I swap these two, are you still getting the same answer? Because language model is like, it has the positional encoding, which means it's like it treats tokens in different positions differently. And this means many language models have the position bias. So when you ask it A or B, it'll tell you A. When you ask it B or A, it'll tell you B. Then you know that it's having this bias instead of spitting out a truthful answer. So usually you want to flip a few times to mitigate the position bias, and you want to take the mode in order to mitigate the variants as well. This paper has more discussions in the self-consistency if you're interested. Yeah, so this is some tricks about evaluation. Another thing about evaluation is that explanation is very important. So this is actually the output from Vertex AI's evaluation service, my previous team's work. So it's like you have a pair of responses, and in the evaluation output, you would output the explanation as well because of two reasons. One is you can treat the explanation as a chain of thought. So you force the language model into reasoning over why this response A is indeed better than response B. And this reasoning step is very important because it breaks down the problem. It decomposes the problem into smaller, tractable problems, and usually you get a more accurate answer. And as a side product, you get the explanation, which you can convince people over. And I know some people inspect the explanation or do a clustering on the explanation to see what problems the language model has. Maybe the language model is too verbose. Maybe the language model has a problem XYZ. So you can all see it in the judge model's explanation and do an improvement afterwards. So this is explanation. Before we move on, any questions or please interrupt? No, we are good to move. We're good to move on? Okay. Okay, perfect. So next I want to talk about hallucinations, fact-checking, and attribution, which is one of the big headaches in RAG applications as well. You see that, so citations, to some extent, it mitigates this, but a lot of people want to do grounding as well. So grounding is saying, take the output of your language model and break the output into small statements. And for each statement, I want to make sure it is well supported by evidences. And grounded, this attribution is exactly doing that, finding evidence for each and every output statement. If you're interested, you can take a look. The paper is RARR, so it's a long title. It's by DeepMind, I think. And what it does is that it does the following workflow. So you have an LM output. It could be very likely it's coming from your RAG pipeline. It's the final answer generated by your RAG. And then you break down the statement, also using an LLM. Once you break down the statement, you have an idea whether the statement is worth fact-checking. For example, I like frozen yogurt. It's not a statement that's worth fact-checking because it's just like a preference thing. But statements like a horse has 5 legs, this is indeed something that's worth fact-checking. So you have a little binary classifier that says, oh, whether this thing is worth fact-checking. Usually it's pretty easy to distinguish. And then you only do fact-checking on those, that are worth to you. In this case, you can filter out a lot of the things already. And then for the statements that are worth checking, you would rewrite it into a bunch of queries that search in the database and see whether they are indeed well supported. So in this case, you would rewrite it into a few queries like, when did Meal in Between premiere? Which channel was this show on, etc. And then you would, given these queries, do another round of retrieval on your database to see whether this output statement is indeed well supported by evidences. Usually you would be able to catch errors and rewrite your answer so that it becomes correct and fix quite a few hallucinations in this case. Finally, and this is the last part of the presentation, and we'll leave the rest of the time for Q&A, is that agents. Agents is pretty important and big, becoming a topic this year. And it's indeed talking about a few topics: tool use, memory, and the reliable execution of a big autonomous system. So let me, sorry.
Just a question, like, can you hear the audio playing just now? Yes, okay.
Let's start with an easy one. In this example, we'll ask Manus to help screen resumes. I've just sent Manus a zip file containing 10 resume documents. Since each Manus session has its own computer, it can work like a human. First unzipping the file, then browsing through each resume page by page, and recording important information to documents. Manus works asynchronously in the cloud, which means you can close your laptop anytime, and Manus will notify you when everything is complete. Of course, you can also give Manus new instructions at any time. Here I've sent Manus 5 more resumes. After carefully reading all 15 resumes, Manus provides the ranking suggestions, along with candidate profiles and evaluation criteria as supporting materials. This is pretty good, but I prefer a spreadsheet. Let's have Manus create one. Manus has its own knowledge and memory, so it can teach Manus that the next time it handles a similar task, it will deliver a spreadsheet right away.
Just now, I believe a lot of you have heard about the application Manus. So it's an agent application that is getting very popular, and we're just now showing a workflow of Manus performing the task of an HR recruiter, screening through candidate resumes one by one, and also giving a rating for each candidate's resumes, and finally give a ranking for all the candidates. So this is a very, very typical and helpful enterprise workflow. Several other enterprise workflows that we've worked with or interacted with are, for example, this is a very important workflow for finance, in particular, checking the invoice. So you have a lot of purchase orders, and it generates a lot of invoices from your vendors. And the finance department, and please shout out if you have the same problem as well, etc. They need to verify whether the invoice is correct, provided by the vendor, and matches what they have received. So it is a long workflow, and it's not an easy task because it involves a few steps, including opening the vendor invoice. So if you are on a computer and it would click open the invoice and do a number of document tasks, and do what they call three-way matching of whether the purchase order matches the invoice, including verifying vendors, item quantities, and price, and matching the receipt with the invoice, confirming like whether I have indeed received such quantity of goods that matches the invoice. And it would do like the purchase order and receipt matching, ensuring like, what I order is indeed what I receive. Sometimes the wrong item would arrive, etc. So the three-way matching finishes, and then if an exception is raised, I would route the exception to an appropriate resolution or personnel, and I might require some other contacts, etc. And at the end, we approve the invoice, or like we not approve and escalate. So this is a long workflow for enterprise agent. Another few examples are healthcare patient triage. The patient triage has a lot of the unstructured data, sometimes handwritten doctor notes. So parsing the handwritten thing into a structured data, and then do a number of triages afterwards, and verifying whether each step is done correctly is also another type of agent workflow. And financial underwriting, it naturally consists of 10 or 20 subtasks. I don't know how many of you work in finance, in bank, or other like known loan providers, etc. Like it has a number of checks it needs to do on the document package that the applicant has uploaded, and then each step needs to be verified the correctness. So those are very complex enterprise agents tasks, and they are complex because of a few reasons. One is the tool use. So I believe a lot of you are working with some dedicated software that are for enterprise usages. And it's a question of how to let your language model be able to use the enterprise software that you are using. You could, of course, build your own connector, but there are also companies that have already built the connectors or MCPs for those enterprise softwares. Like here I'm taking a screenshot from Composio. So Composio is a startup that has integrated, I believe, tens of thousands of tools into its platform. And instead of handwriting your own connector, you could directly use it. So it has like integrations with HubSpot, CRM, Salesforce, with Google Calendar, with Slack, etc. So a lot of the connector providers as well. In addition to such startups like Composio, public clouds like Azure and also GCP. I didn't check AWS, but I believe they have the. But I believe AWS would be like similar as well. They have the connectors that are pre-baked that connects to a lot of the enterprise software already, and they are ready to use as tools by the language models. The challenge with tool use is that there are many tools, as we have already said in the beginning, that for enterprise it's not a question of tens of tools, it's 500 tools. Because remember, like every function is a tool. Every function is a tool use. For example, in Salesforce, if you want to have a workflow of creating a customer entry for your company, then the function of creating a new customer is itself a tool. There will be another tool for like deleting a customer. There'll be yet another tool of updating a record of interaction with a customer, so on and so forth. So this gives you many, many tools, and this is the difficulty. How to mitigate? RAG is some of the what some people rely on, of only retrieving the relevant tools for a specific task. So for example, if I am just adding a new customer, like all of the other Salesforce tools are completely irrelevant to me, so I would expose the language model just into a limited set of tools that are relevant. Some language models have this RAG system baked in the case that you upload a ton of tools, and it'll automatically take care of getting the most relevant tools and stuffing the tool into the developer instruction itself. So it differs from model to model. If you're using a open source model or some model that obviously doesn't have this mechanism baked in, please take care of it. But if automatically the language model can already do so, then in this case you wouldn't need to. Another route is to use reinforcement learning to train on tasks for workflow proficiency. You would almost like view it as shape a college graduate who is a generalist into a specialist that is extremely familiar with that domain. So that means that it is exposed to a number of tasks. For example, it's just doing search and reflection on that particular medical domain, or it is just in charge of the workflow of adding a new of managing customers using Salesforce, and it doesn't know, like it doesn't care about other things at all. So this type of like specialized RL agents with a limited tool set, and it has good proficiency on how to use the tools, is kind of like baking it into the muscle memory of the agent. By agent, I'm all just referring to the LLM that's in charge of planning and orchestrating all of the tools. So this can be, again, achieved by careful design of the reward and the task. For example, your task is just the success of adding a new customer, updating all your system, etc., and you kind of have a final reward that is clearly defined for task completion, then it is very safe for you to use RL to improve your agents just to accomplish that task. It boosts a lot of stability, reliability of the task completion usually, because usually what you find is that, okay, the language model, the agent works like 70% of the time, but not every time. This is not very tolerable for a lot of the enterprise use cases because it is rigid and does not tolerate this type of mistakes. So in this way, you might want some fine-tuning on top of the agent to be able to boost its accuracy of task completion to a higher amount. Another two, I want to, last topic is two open questions in the agent world. One is memory, the other is long trajectory. So first about memory, memory is becoming a very important topic, especially for personalized agents. So imagine that you have a user that has a medical history that you want to tailor your response with his or her medical history. So what happens is that the user has interacted with your platform for a while, and you should be able to extract from their past interactions about whether they have some conditions or whether they have some preferences or what have you. And there are quite some offerings on the market about memory. There are good and bad about each offering. I believe Mem0 is one of the open source offerings for memory, but also there are enterprise offerings like Vertex. So Google Cloud Vertex just have this memory bank offering a few days back, I believe, and that automatically manages the user's memory on your platform. It's a black box, of course, but you kind of have the memory writing and memory retrieval automatically taken care of for you. So this is memory. The other thing is this diagram is just showing how to insert new memory, merge existing memories, and retrieve memories for your use case. And another difficult problem is how to reliably execute long trajectory tasks. And this is difficult. The reason is because enterprise tasks are pretty long trajectory, and humans have a good idea of how to do it. Like, first I do this, next I do this, and 10 steps later, I finally do that. This is a very difficult thing for agents. The reason is you could imagine it's an explosion of the action space, and the action space is getting exponentially large with respect to the number of steps that you're exposing the agent to, because you can imagine the number of in each step, the branching factor is K tools that you give it. The next step is again K tools that it needs to choose from, so on and so forth. This makes the action space extremely large and hard. So this becomes a problem of the agent. Usually it will fall off somewhere in the long trajectory execution. Maybe you're lucky if it falls off at step 20, but if you're unlucky, like it falls off very, very early on and doesn't make the system very stable. There are patterns of repeated tasks. We saw a few patterns already in our earlier description of today's presentation. Like a typical pattern would be search and reflect. This is a deep research pattern. I search, I reflect whether I have a gap in my knowledge, and then I search again, and I reflect again, so on and so forth. So this is a very typical loop. And another common loop is browser agents. So you see those browser agents who completes tasks for you or even scrapes information online. So let's say you have a competitor, you want to watch their price or watch their behavior every day, and you would have a browser agent that clicks through the links every day and to extract information about your competitors over and over again daily. So what the browser agent does is it browses and extracts information about your competitor, browses again, extract again, until it reaches the end of its tasks. So this is yet another very typical loop for a web agent as well. There are tools like browser use, etc. Happy to talk more if you're interested. But those are repeated tasks, and those are constituting like unstable execution. So one way is actually to, and this is relevant to what my new company is doing as well, is that can we collapse the loop into a more compact model? The reason is that we all experience some sort of deep research, and it's taking like 10 minutes to complete, or 3 minutes if for more shorter deep researches. But really, it's what's taken so long, if you ever implemented a deep research system, is this loop is taking very long. If I search, I gather information, and I search again, etc. And you repeat for 5 times, and finally you come up with a final answer. And this loop has taken very long. But if you look at this loop and think about it, is that the input space and the output space is actually very fixed. the input is like information, the output space is the search result and also next step action. So given that the input and output space is pretty fixed, we can very well train a compact multi-step model. I mean, a small multi-step model specialized in just these tasks. It doesn't need to be too smart because it's just doing this like information collection and reflection step. It does not need to do how to do Olympiads, math, etc. So it's like limited, very limited to this specific skill set. And this means that we can like get rid of a lot of the functionalities, and we don't need a huge gigantic model in order to do this. But also, if we do a post-training on it, if we do RL on it, then it can become extremely specialized on this type of input and lowering the cost by a lot. But by cost, I mean computation cost, but you could like translate it into time, latency as well. And a lot of times it's achieving higher quality. And the reason it's achieving higher quality is that you're baking it into its muscle memory. It's not like it's not that big of a variance every time it executes because it's practiced on this task for so many times. So this kind of shrinks the uncertainty of the output quite a bit as well. So that's what I'm saying. It's almost like for those of us that came from like, old world of computer science, it's almost like a compiler for agents that's collapsing a number of frequently used actions into a more specialized, optimized kernel that it can be executed on. Yeah. So that's the launch trajectory problem and the memory problem that we mentioned earlier, and that constitutes our sharing today. I'll leave the last 20 minutes for questions or more open discussions.
Thank you, Bethany, for the